Welcome to the TWIML AI podcast. I'm your host, Sam Charrington. Hey, what's up, everyone? Happy Memorial Day to those of you in the States. Although we might not be able to celebrate holidays like we once would, I encourage you to find a way to enjoy yourself this weekend, connect with family and friends, and enjoy some good food and fun as best as you can. I am super excited to be hosting tomorrow's live panel discussion on advancing your data science career during the pandemic. This is going to be a great one, featuring an amazing lineup, and I encourage you to join us. You can check out twimlai.com/dscareers for more information and to register. I also want to give you a heads up regarding my upcoming webinar with Algorithmia CTO Kenny Daniel. The hot topic at last year's TWIMLCon Unconference was a discussion on whether you should build or buy an ML or data science platform. Well, we'll be tackling this topic head on in our upcoming session. We'll discuss what goes into building a machine learning management platform, how to make the business case for ML ops at your company, and how to evaluate off-the-shelf machine learning management solutions. Be sure to mark your calendar for 10 a.m. Pacific on June 9th and visit twimlai.com/algorithmia to register. That's twimlai.com/algorithmia. All right, enjoy the show and enjoy the holiday. All right, everyone, I am on the line with Joey Gonzalez. Joey is an assistant professor at UC Berkeley in the EECS department. Joey, welcome to the TWIML AI podcast.
Thank you for having me.
I'm really looking forward to diving into this conversation, and in particular talking about ML systems and your recent paper on train large, then compress. But before we do that, please share a little bit about your background and how you came to work in ML and AI.
Yeah, excellent. So my story is a bit funny. I started my PhD at Carnegie Mellon with an interest in actually flipping helicopters, because that was a trendy thing to do back in 2006, a while back.
Flipping helicopters?
Flipping helicopters.
Like buying them, fixing them up, and selling them?
No.
Or
the more interesting one. You fly them and then flip them. Actually, a colleague of mine, Peter Beal, now at Berkeley, when he was finishing up his thesis work, he was looking at how to do interesting control for helicopters. I thought that was really cool. And I at CMU, I was I went to my thesis advisor, and you've worked on control as well. I'm kind of interested in flipping helicopters. I think that's really neat research. And I'm
interested know that in was networks.
A thing. It was, and it actually was some of the pioneering work to what we see today in reinforcement learning. But what's kind of cool about this story is my advisor at that time, being a real machine learning researcher, I was like, flipping helicopters, that's exciting, but there's something more important. Like we can actually help the world with sensors. We can build sensor networks to monitor fires, and we can use kind of principled machine learning techniques. I should add that when I was looking at the flipping helicopters, I was like, we should flip them with neural networks. And the other thing my advisor said, which was good advice at the time, was neural networks aren't really serious research. We use more statistical methods, graphical models, things that have formal foundations that we can reason about and write kind of detailed analyses and understand what our models are doing. And that was good advice. And so I went down this path of how to build Gaussian processes, Bayesian nonparametric methods to reason about link quality and sensor networks. And in that process of doing that, I kind of stumbled into a problem. I was writing a lot of MATLAB code to compute big matrix inverses and then approximations to that to make it run faster. And one of the things I enjoyed doing in the process of exploring these more efficient MATLAB programs was trying to make them more parallel. And I think my advisor clued in. He's a good advisor. He's like, maybe you enjoy that more. So maybe instead of focusing on the nonparametrics and the sense networks, let's start to think about how to make machine learning more efficient. And in particular, at that point in time, Hadoop was taking off. And so we were like, MapReduce, that's going to change machine learning. And we were thinking, well, we're working on graphs and they just don't fit the MapReduce pattern. And the kinds of computation we were doing it didn't actually fit with the technology that people were building. So we started to explore a different design of systems. So a design of systems for computation on graphs, which took us down the design of graph processing systems. A system that I ended up writing as kind of the end of my thesis was GraphLab for doing very large analysis of graphs. And so by the time I finished my PhD, I was actually writing systems papers, not machine learning papers. And the field was changing very, very rapidly too. This is around 2012. And if anyone's been following the history of machine learning, around 2012, everyone started to realize maybe actually the neural nets were a good idea. The deep learning, these ideas actually really dated back to the 1980s. They're actually really starting to work. And they were changing the field of machine learning. And graphs were also taking off. So we built actually a company around the systems that I was developing as a graduate student. It was GraphLab. That evolved into a company for building tools for data scientists to do interesting machine learning at scale. That was ultimately acquired by Apple. And around that time, I also joined the UC Berkeley AMP Lab as a postdoc. And there was a chance to come out to California, and it was a really exciting opportunity to do research in a different system, a system called Spark. Which eventually became Apache Spark. And there we started to develop the graph processing foundation for the Apache Spark system. And again, as I started to explore more and more into the field, I learned more about research in data systems and transaction processing and how those connect back to machine learning. And so after finishing my postdoc, I came to Berkeley. In fact, I chose not to follow the much more lucrative path of the startup.
I was going to ask about that.
Yeah, I made a terrible financial decision, but I'm happy because I have a chance to work with students. I'm a little less happy because I'm not as wealthy as one could have been. But now I am teaching students that do research at the intersection of machine learning and systems. And so we have a pretty broad agenda around how to build better technologies for delivering models, to manage the machine learning lifecycle, not just training, but prediction. How to prioritize training experiments on the cloud, to use serverless computing to make machine learning more cost-effective and easier to deploy. We have a big agenda around autonomous driving, building the actual platform that supports autonomous driving, not necessarily the models, but how they are connected together to make a reliable car. And we have work in natural language processing and computer vision. And one of those papers, one that I'm hoping to talk a bit about today, which is our work on making BERT models easier to train. And it too has a kind of funny story how we came to actually a realization that what we were thinking was entirely wrong. And that's what that paper talks a bit about.
Well, we'll get to that funny story in a second. There's so much interesting stuff that you just mentioned. There are at least 3 or 4 interesting podcasts in here. I'd love to dig into some of the stuff you're doing with serverless at some point and how that intersects with ML and AI. It's something I've looked at a little bit as well. But before we jump into even more of that, I'm curious. Your co-founder at GraphLab and Turi, Carlos Gestrin, was one of my very first guests on this show, TWIML Talk number 7, in fact. And I'm curious how you came to know and found the company with Carlos.
Yeah, Carlos is awesome. So he was my thesis advisor.
Awesome. Okay.
When I came to CMU, Carlos was the guy who said, "Let's not flip helicopters. Let's do something that could make an impact in the world." And he was a great advisor. Like he pushed me down the right path in my PhD, the thing that reflected what I was interested in. And he is one of the pioneers in the modern field of machine learning and systems. Yeah, and so that's how I came to know him.
He did go to Apple.
He did.
I saw him recently at NeurIPS, most recently in Vancouver, and seems to be really having a good time there.
Yeah, he's had a chance to have a lot of impact doing really cool stuff.
You kind of laid out this broad space of research. It sounds very broad, actually.
Yeah.
Tied together by systems. I'm curious how you kind of, is it rationalized by, hey, you've got a bunch of, students and you're letting them flip helicopters in the way that they want to flip helicopters more so than you were, encouraged to do, or...
All right. So it's challenging as faculty to decide what is your research agenda. And one likes to imagine you sit there and go, here are the two things I want to study. Usually not one, because you have to have enough for a couple students to build their thesis around. The reality is that students pull you. And I think sort of like artists, it's hard to compel people to follow the research agenda that you ultimately want. My advisor did a great job. It's not about telling you what to do. It's about showing you the exciting opportunities you can explore. And so with my students, I've pushed them in directions to think about how we make models more efficient to not just train, but to serve. how we support new emerging applications of machine learning that might require innovation both in the system and the modeling techniques. And actually, what's kind of neat about the field of systems and machine learning is, again, when I started, it wasn't really a thing. In fact, some of my colleagues at CMU were like, you're just hacking. You're not actually doing research. You're not proving anything fundamental about machine learning. You're writing software. A little bit of that was true. We were definitely writing a lot of software. We were trying to prove some stuff too. But I think the impact might have actually been more on the software side. And one of the funny things about the broader field of systems and machine learning is that it actually has been kind of the undercurrent of a lot of the recent progress in AI. When we look at this revolution in deep learning, we can go back to the 2012 the AlexNet paper. That's actually not the beginning. It goes way back to the 1980s. In fact, the techniques are from the 1980s. The architectures, the models, even the algorithms that we're using are from the 1980s. If you actually read the AlexNet paper, more than half the paper is devoted to how they got it to run on a GPU, how they got it to run on a very large image data set, and some of the optimizations they made to the training process to make it run at scale. So it is the movement to scale that really helped launch the revolution that we are on today. And now there's the other factor, which I think people overlook. And it's sort of, when I was doing my PhD, we were writing the Fortran of machine learning. We were writing MATLAB code to implement algorithms and debugging gradient procedures, and that's absurd. Today, it's just too easy. So a graduate student can pick up PyTorch, TensorFlow, MXNet, one of these packages, and very easily architect a new model and train it on TPUs, GPUs, hardware they barely understand, and get it to run at scale on data sets that they don't have to collect. So that is an enormous jump forward. And if you look really carefully and a little bit depressingly, the models didn't change that radically. The algorithms didn't change that radically. What changed was it became a lot easier. We developed the languages, the tools to make machine learning practical. And that really boiled down to getting the right abstractions. And maybe if you roll all the way back, when AlexNet came out, they didn't quite have that. But right after AlexNet came out, Theano started to really take off. Caffe at Berkeley started to take off. And it became so much easier to build that next model and the next model and so on. And today we're stuck in like a flood of archive papers because basically anyone can download one of these packages and start building state-of-the-art machine learning models. There's some learning that you go in the process, but the fundamental principles are define your objective, define your decision process, and then tune your decision process, optimize it for that objective. That's it. And the undercurrent that drive all of this has been a lot of the innovation in the systems front, not necessarily the machine learning. And so my research is trying to find those right abstractions, and especially as we look at new frontiers, not just training models, but how we deliver them, how we support them in autonomous driving, and how we adjust the architectures of the models themselves to make them more efficient in these new kinds of applications.
Yeah, when I first started doing these interviews, one of my favorite questions was looking to explore kind of the way folks came up with new models and trying to find the kind of science behind it. And I think that the takeaways were a lot of it was, the answer was like graduate student descent. Like, we would just throw a graduate student at this and, they tweak something that pre-existed, but there wasn't necessarily kind of a hard science behind how to come up with a new model architecture. But still, we've seen a lot of, innovation, like in around, BERT and the kinds of transformer models that we're seeing here. Would your answer to that be kind of similar? Has it, it changed a lot? Or how do you think of, beyond kind of that high level process you just laid out, how do you think of the process for coming up with these new types of architectures?
Yeah, so that's been a struggle for me. So remember, I start with this religion, this Bayesian philosophy of model development. They have these principles of priors and likelihoods that gave us at least the basic foundations of what to think about when building a model. That's all. That's not gone, but that's effectively gone for a lot of the machine learning world. And so we're left with
but coming back though, actually, right? Like the causal modeling is on the rise, I think.
So I should say it's not gone. And it's very important to note that a lot of the world actually runs on these more traditional techniques. It's the research community where we're writing these new papers for language modeling or speech or driving, where there's very specific cases that have been kind of dominated by deep learning techniques. But the Bayesian methods are still fully alive in medicine and in even traditional advertising algorithms. But with that in mind, so when I start to look at the deep learning work, how do I find those principles? And actually, they actually exist. They're a little smaller, and sadly, we start to embody the model with personality. Like the model is trying to do X, which is sad because that's not how we like to formally think of things. But these building blocks, convolution, recurrence, attention, each of these becomes tools that we can use to architect our models. When students go, how deep should we make it? Well, we try to go a little deeper. They start to look at how it affects convergence rates, variation in batch size, and its relation to batch norms. We have little rules of thumb. And unfortunately, there's no great, my PhD students take 2 or 3 years to get up to speed with the rules of thumb in the area that they're working in. And once they have that, I hope they teach the next PhD students and so on, because it's hard to really grasp what those are. It's more like it comes from experience working with these models and going, right? So like the transformer in this particular piece of work that we've been exploring, like how to make it more efficient, we're like, should we make it deeper? Should we make it wider? Who knows? So we start to measure each of these things. And that's one of the jokes that we make, is that machine learning has become more like a biological science. It's driven by laboratory experiments, by using compute to understand better the models that we're building, as opposed to the more principled approach we might have had in the past. We tried to frame it in some probabilistic architecture.
You mentioned that there was a story behind the work that led to train large, then compress.
Yeah, so I'm happy to go into that story.
Sure.
Yeah, so the story behind the train large and compress work, it starts in the following. So we've been doing a lot of work in how to make computer vision models more efficient, in particular, not for training, but for inference. And so we have these SkipNet architectures, ways of making things more dynamic. And some of my colleagues go, you know what, maybe we should start thinking about language models. They seem to be eating up a lot of cycles. The transformer, the BERT model that's become a kind of a foundation for reasoning about text and context. Well, so that model is pretty expensive to run. And so we said, all right, maybe we'll explore what we can do in the context of making these BERT models more efficient. Now, I should say a lot of people are starting to think about that because BERT is incredibly expensive to run on text feeds, and text is a pretty large body of data that we might want to process.
Yeah, I'll mention that for folks that want to dig into that particular point, I did an interview with Emma Struble, who has in a fair amount of detail, kind of characterize both the cost and kind of environmental impact of training some of these large scale NLP models. And it is crazy.
It's crazy. Actually, the CO2 narrative was one of the things that got me, especially I was, maybe we don't touch language. There's plenty of people thinking about it. And then I saw Emma's paper. It's like, wow, I'm here trying to make autonomous cars so that, a little bit more environmentally friendly when it comes to driving, when I could go fix a fundamental problem right in my field. So we look at these language models and go, how can we make these better? And the first step to doing that is we got to understand them. So we need to run some experiments. And my students go, well, we're going to need a lot of machines. I can't afford a lot of machines. So if I look at Google, at Facebook, they can throw a lot of compute in trying to understand something. And that's actually one of their tools that we don't really have access to. We've actually started a collaboration with Google so we could get access to TPUs, but we can't do it at the scale that they're going to run their experiments. So we had to get lean. So how can we rapidly iterate on variations in our architectures? We want to look at different types of attention, different architecture sizes, understand the effects of these hyperparameters. And so my students go, well, here's what we'll do. We'll make the models really small, and we'll run a training run every day with different configurations, and we'll get a good picture of what's going on. And they did that. And so they made the model really small because that would, in theory, make it really fast to train. But they also
really small in terms of number of parameters, or
so they made the model smaller in terms of both the height, the number of layers, and the width, the number of these hidden layers, hidden parameters inside of each of the attention heads. So basically, they tried to make the model so it would train faster because it had less to compute, less to update. This is more of a classic way of thinking. How I would approach the problem too. If it's too big, make the problem smaller. It should go faster, right? It's less to do. So they did that, and it was working. But one of them was like, all right, well, what if we make it a little bigger, just to get a point of comparison? And they applied the point of comparison on top of the smaller models they were training, and the point of comparison seemed to go down pretty quickly. And I said, well, let's put it in time. And you put it in time, and actually the bigger model, the point of comparison, was actually getting to a better accuracy quicker than the smaller models that we were supposed to be running because they were faster to train. And then we started to wonder, maybe it's the other way around. Maybe we had this backwards all along. And if we want to go faster, we have to make the problem bigger, which is really counterintuitive. But it actually turns out to be a really neat intersection between how these models converge, and how they can take advantage of parallel resources in the GPUs and TPUs to get good scaling as we make them bigger. And that sort of forms the foundation of this work that sort of went against what we thought would be the case and actually presents a neat way to approach training these expensive models.
Is the idea related to the kind of the rate of change of kind of accuracy for these models, and taking advantage of the idea that the larger models learn quicker, but I guess the area under that learning curve is proportional to your compute costs, and you can kind of optimize that?
Yeah, so there's a bunch of trade-offs. I try to walk through them because they were counterintuitive to me at first too. So the first trade-off to think about is, actually, let's talk about compute. So as I make my model bigger, I'm going to compute more. So that's more work and it should run slower. But the neat thing is that when I make these models wider, at least, I actually expose more parallelism. And if we look at the execution of these models, it's a little surprising. We've optimized those GPUs and TPUs to have a substantial amount of compute, often for computer vision models. And so now we have an opportunity when we run a transformer, if we don't crank the batch size up incredibly high, we actually have a fair amount of leftover compute that we can use. So making the model bigger doesn't necessarily translate to a linear increase in runtime. So we can afford to make the models bigger without linearly increasing execution.
Parallelism and runtime don't correlate to cost because you're just running more compute at the same time.
Yeah. So this is looking at a
or carbon
GPU.
For that matter.
Yeah. So, all right, you're getting to the interesting stuff. So first, let's, in the paper, we actually tried to control for this. I was like, hold on a second, you're just going to increase the cost of compute. So we looked at one GPU, and what happens is you're not using all the cores on one GPU when we were looking at the smaller models. So as we make the models bigger for a fixed batch size, we can get an increase in the utilization of the GPU. And right now, it's not easy to turn off those cores. And you're also paying a fixed overhead to power the actual box that the cores are living in, plus cooling. So trying to power throttle individual cores on GPU is generally not a great idea, especially if we can get better utilization of the cores that we have. Now, you could say, I should have more GPUs. We did. So then we look at more GPUs. We're going to burn more resources as we turn on more GPUs. But the hope is that we can get to a solution quicker. And if those GPUs are already attached to our box, which they often are, there's usually some incentive to go ahead and try to use those as efficiently as possible. And so that brings us to the second question, which is, if I make my model bigger, is it really improving in efficiency, which is what we'd like to think of as the improvement in our perplexity, or reduction in perplexity as we train. And so we'd like to reduce our error as quickly as possible in wall clock time, because we have to pay for the power of the building and so on. So we want to train as fast as possible in time. The simpler way to look at that first is how is the perplexity or error decreasing as a function of the amount of data that we touch. And so there are two knobs there. So now we're getting into the weeds, but there's the batch size, which determines how much data we look at per step of our algorithm. The more data we look at, the better of an estimate of the direction that minimizes the loss, which in principle should give us faster convergence. It also increases GPU utilization, so we can use that as another mechanism to get better utilization out of each of our pieces of hardware. But it also has diminishing returns. So as we increase the batch size, our speed at which we're able to converge as a function of samples we look at doesn't necessarily increase linearly. And one of the other sort of side effects of this, which if you work in computer vision, you're like, oh no, there's a problem, that as we increase the batch size, there's some risk of overfitting. And this is an effect that shows up more in computer vision models where it's somewhat data poor, where in NLP, it seems at this point at least, that we have opportunities to overfit more before we actually are properly overfitting. So there's this question of the generalization gap, the gap between how well your model is fitting the training data and the test data. And in NLP tasks, we're not at a point where that generalization gap is disappearing, which means that we can increase the batch size quite a bit more without overfitting. But it also means we can increase the model size quite a bit more. And so what this paper then does is tries to play off or compare this trade-off between model size and batch size to find the best combination. And one of the neat results we find is that actually cranking up the model size and the batch size to a certain extent as well kind of gives us the best outcome. It gets us to a model that's more sample efficient. The more samples it sees, the faster it reduces the test error. And it also lets us better utilize our hardware. So we're actually getting a gain from parallelism. And those two forces interact to give us a faster, in terms of wall clock time, reduction in the task perplexity or the error metric that we care about.
In terms of this generalization gap and the differences between what you see in computer vision and what you see in NLP tasks, is that related to the way the problems are formulated in terms of supervised versus self-supervised, semi-supervised, and the kind of availability of data and labels and that kind of thing?
Absolutely. So you're hitting a key point. So in computer vision, we're largely still focused on supervised tasks. We need labeled data sets, which are big, but they're not as big as we want them to be. Whereas in NLP, we can go to really large unlabeled data sets because we're essentially predicting missing words. So we've created this self-supervised task. And that means that we have so much more data, we can support bigger models and bigger batch sizes without having this generalization gap disappear. We're able without eliminating or causing our training error to go to zero and our test error to dominate. So there is this opening created by this self-supervised training that we're able to take advantage of. Now, in our experiments, we test both the self-supervised training task as well as the downstream translation or classification tasks that would be applied to actual language modeling, the supervised training tasks. But that's typically done as a small fine-tuning step on top of this extensive pre-training, which is where all the CO2 is going to pre-train these models.
And then in your description of the train large, it sounded a little bit like you're ultimately saying, fully utilize whatever box you're training on. But there's a lot more nuance there, I am sure. Yeah. Elaborate on that.
So this has been a big question in data center design generally. As a systems person, like, should I turn off my GPUs? Should I turn off my CPUs? Or should I try to utilize them better? And the general consensus when we think about data centers is that we really do want to try to maximize our utilization. Part because we bought the data center, it's expensive, we should use it. We have to keep it cool, we have to staff it. There's a lot of other factors that go into play. And so we want to be able to use that hardware as much as possible and as efficiently as possible. And part of the reason we might want to use it as efficiently as possible, you think of things like serverless. If I'm not using the hardware, I can put something else there. And we're creating markets for filling in the excess capacity. So the idea that I would turn off a GPU is sort of silly. I should always have something running. Now the question is, can I make that thing running on the GPU as efficient as possible? And so in our work, we're focusing on trying to maximize that efficiency. In my lab, for example, students are competing for the GPUs. The one GPU experiment's definitely easier to run because they're not fighting for the entire box. And so the other GPUs are being used for other experiments. And then when we go to 8 GPUs, we're going to again use the whole box. So the general consensus, or at least the thought process today when we think about the data centers, to really maximize our utilization and not try to power throttle or limit the performance of each of the cores. Now, it could be in the future, new kinds of hardware might change that trade-off. But the underlying economics would sort of suggest that if you bought the device, you should really try to find ways to maximize its usage. And given machine learning has an infinite supply of things that we'd like to train, it's not hard to imagine that I can always fill my excess capacity with more training.
So is the paper fundamentally an economics paper in the sense of, you're trying to maximize utilization and those kind of things? Or do you also get to results that talk about performance given a set of constraints, like your traditional computer sciencey kinds of papers?
Yeah, so it's funny. We hadn't gone down the economics route, so it's a fun conversation.
I mean that very loosely. You know?
Well, so we are actually very much thinking about the economics of computing. When we look at serverless, that is going to fundamentally change our economics of computing in a way that I think will make things more efficient, more cost effective, and actually easier. So it's a win for everyone. And we actually have a upcoming paper on this at Hot Cloud about the economics of serverless are going to generally be favorable for everyone, assuming we get some of the systems problems ironed out. This paper was really our students as a first effort to really make progress in the BERT pre-training space to find mechanisms that we in academia can use to go fast. And part of that is finding better ways to be more efficient about training. It allows us to run experiments more quickly. And so we can now innovate on BERT. And one of the things we're actually looking at is trying to make these models more non-parametric so they can leverage other data sources. one of the side consequences of this paper is sort of a, if you're out there thinking about, that's really cool, I want to deploy that. But hey, wait a second, you made the model 4 or 5x bigger, 6, 7x bigger. That's expensive for inference. What am I going to do about that? And in fact, when we got this result, that was like my first conclusion. Yay, we went on the training front, but we just made inference, which is actually the more expensive problem, worse by 7, 10x. And if you think about it, training should only be a small part of the use of these models. Inference is where really the cost should be. And it is when you look at practical applications. Over time. We might train it, but we're going to run that model 24/7 at every single tweet, every single web page that we encounter. That's a lot of inference. And V100, so you're doing 1,000, one batch should optimize 1,000 sentences per second, which sounds good. But then you think of the amount of text in the web, that's a lot of expensive GPU hardware. So making the models smaller after training was one of the questions that we had to solve. And so sort of the second half of this paper comes back and goes, wait a second, so we made the models bigger to train faster, but now we need a way to squeeze them down. And maybe actually the bigger insight, which is also maybe a little less counterintuitive, is that the bigger models we could actually make smaller more efficiently and actually with less of a degradation in accuracy. So we train a really large model and then we chop it up. So we both explored weight pruning, so eliminating weights, making the model more sparse, and quantization, reducing the bit precision of each of the weights. And so we are able to take our much larger models and then apply these compression techniques to make them smaller. And the effect of that is we can make the model actually smaller than the small models while retaining higher accuracy. And so that's something that we're still trying to explore.
Were you able to use the compression techniques off the shelf, or did you have to adapt them to this kind of model or the specifics of the way you train them?
Yeah, so getting close to the deadline, realizing our models are now 10x bigger, we're like, all right, so how do we quickly figure out how to compress these? Good news. One of the students, Shen, who's working on this project, had just finished a work on quantization. And so we were like, all right, Shen, can we use your quantization technique? He's like, I don't know, maybe. And so he started playing around with it, and it turns out that actually worked really well. And so we looked at the standard quantization and standard pruning. So we tried not to innovate extensively in each of these pieces, more of an exploration of how they interact with this kind of counterintuitive hypothesis that bigger models might actually be better, both for training and it turns out for inference as well, if we compress it.
Got it. So not that you have any of these numbers like right at your fingertips, but can you give us a sense for when you say train large, like what large means in this case and how that compares to what a Google might do typically?
Yeah, so I think we were looking at like 6x, 7x bigger than was normally published. I'm guessing Google actually goes much larger still, and they might already be benefiting from these ideas.
And what order of magnitude is that in terms of number of, servers or CPUs or GPUs or? So
we were at 8 GPUs. We actually also ran experiments on a TPU, a V3 TPU as well. I'm trying to remember the exact sizes. I have a paper in front of me if I can find it. Many tabs. Yeah, so I think we were up to like 20 hidden layers or so. Or 24. Went up 24 layers. And we tried hidden sizes of like the order of 1536. So 1,536 hidden units for each of the layers. So we tried a pretty reasonable space. We built off the Roberto work, which is actually, if people haven't looked at, is kind of neat, sort of revisiting what Bert did. And in some ways, Bert really had the right answer. Just this broader experimentation of the trade-off space makes a big difference. So we built off of that and tried different variations on the sizes described in that paper.
Yeah, the kind of rough magnitudes that I remember reading about, and I don't remember if this was, Bird or Elmore or some of the different variations or Roberta, but there was, on the order of like 64, tens of GPUs for, a week or more.
No,
right?
so we we used a TPU cluster for our big experiments. So we actually tried to reproduce the Roberta setup. So our comparisons are compared to these standard baselines. So we had to use a TPU cluster for several weeks. It's expensive to run the full experiment for the baselines. But what was neat is by making the model bigger, we could get comparable results quicker. Yeah.
Mm-hmm. And so we've kind of characterized bigger, now characterized quicker. What did that mean in practice?
So we used I guess at about 100,000 seconds, we were able to get fairly competitive accuracy. You should see the final number. So it sort of depends also on which tasks. We also accounted for the downstream fine tuning that you'd need to do as well. I don't actually remember off the top of my head.
Well, we'll leave it as an exercise to the listener to pull up the paper. So you've increased the size of the model and the number of resources, the CPU resource or GPU rather resources that the model is running on, and in turn decreased the training time of the model and the aggregate compute cost.
Right.
Did you need to do anything special to accomplish that, or is the paper primarily observing the fact that in aggregate you could the preferable approach is to increase the model size?
So we did small changes to where we placed the batch normalization. We did pre-normalization, but it's like negligible changes in the underlying architecture. Most of it is really exploring this trade-off space, these different parameters. So in some sense, it's a first step towards a bigger agenda. It wasn't intended to be like a ground-changing work, but what's kind of neat is it does really make us at least rethink how we approach training of these models.
Well, it's important stuff. Like I think a lot of people will think, well, if Berkeley's worrying about the cost of training these models, what hope is there for, my lab in, a non-Berkeley institution, that has such close ties to Silicon Valley and relatively awash in resources. And so if you can figure out how to make training these models more efficient, then that's potentially a huge impact for a lot of people.
There's an important sub-narrative here, which is that pre-training isn't something that everyone needs to do. So Google's done a great job of offering these pre-trained models. So this really expensive part isn't something that every group in the world has to address. And that's a good thing. But if we want to innovate on that pre-training process, if we want to do research in it, or we want to, in fact, data suggests that adding more data that's specialized to your domain can improve the quality of the model. So if we want to be able to push pre-training research forward, we do need to find ways to make it more efficient. And I should say, we started out with thinking, we're going to invent a new BERT. And we discovered in the process that maybe we don't necessarily need a new BERT yet, but maybe approaches to how we do the training, how we choose our hyperparameters can make a really big difference.
Your comment just prompted a thought. To what degree has the theoretical trade-off space around pre-training versus fine-tuning been explored, so that, if I know that I have a unique domain, and some, corpus of documents or data available to me, is there any kind of concrete research I can look to help me understand, if I should be pre-training from scratch versus fine tuning, or do I just need to try everything and see what works?
The try everything is not terrible advice, but here's what I would tell my students. So pre-training is expensive. So maybe start with fine tuning. Understand what is your prediction task, and this is what the practical world will do. So take your prediction task, whether or not it's translation or sentiment tagging, or maybe it's like which call center, which call person should this message be forwarded to. Focus on fine tuning for that task first. There's a little bit of art in choosing learning rates and stuff to get your fine tuning to work. So go through that process. Understand how well you can do by fine tuning to your domain. And then if you have, and you might, billions of call records from the past, you think you could really better improve the underlying representation, you could then try to go back to this mass language model training, the pre-training process. And then the work that we've done and other work that's going on around us can help to make that process more efficient, so that you can, in a matter of weeks or a week in our case, take your V100 box and really make substantial progress towards a pre-trained model that's now pre-trained on your domain as well.
And so where do you see this line of research leading?
Yeah, so I ask my students this every day. So as we sit as a group, like, what's next, guys? So we figured this out. The original goal was to be able to develop a new BERT. So now we have the tools to start testing pre-training. What should we do next? One of the things that I'm kind of excited about is the realization that we're trying to cram a lot of knowledge in the weights of our model, and making the models bigger certainly helps with that. Another way to deal with knowledge is to not put it in the model at all. I actually have to look up stuff most of the time when I want to remember facts. I'm terrible at remembering facts. So I use the internet. I have a neural net in my head. It doesn't have to memorize the internet because I have the internet. So having access to a knowledge base can make a big difference in how much we need to encode in our model, making our model perhaps smaller. The ability to synthesize decisions or to apply logic on top of knowledge bases seems like a really big opportunity for language modeling, for NLP broadly, and maybe even for these basic representations like BERT. And so we've been looking at and starting to look at, and there's some other groups actually got some early published work on how to bring in a non-parametric or semi-parametric lens on these models so that we can reference into a large knowledge base in the construction of our embeddings themselves. And that has, the advantage of maybe being more efficient, allowing us to grow the knowledge base without having to retrain the model. We could get more data. Our model just gets better without having to adjust the model itself. And maybe even giving us some explainability. So when we go to make a prediction about like how we embedded the sentence or how we represent this, this decision for which call to route to, we can now actually point back at historical data and say, here's the data we used in our embedding to reason about that. And you can go, oh, that's terrible data. I don't want that in my data set. Or, that makes sense. And so that connection to the data could actually also help with explainability. So that's sort of the vision that my students and I are pretty excited about right now.
Does that pull from or kind of lead you to like memory-based networks or like information retrieval types of problems? Or
Yeah. So memory nets, IR, all of these kind of, let's say IR more classic, memory nets also increasingly more classic. So those are our tools. One of the things we're looking at right now is something as simple as like, can we use embeddings from other pieces of text and simple text similarity to recall those embeddings? And there's some other work exploring this now. Ultimately, things like memory nets or mechanisms to point into a knowledge base and attend to an entire corpus would be really exciting. And we're just starting to explore this. So there's a lot more to do. It does push us in the direction of IR. Imagine a neural net that can Google stuff for you to answer questions. So it certainly, there's a well-studied area that we'll have to build on.
You touched on explainability in there as a possible benefit here. I'm curious about, maybe you elaborating on that a little bit more. And then also you've been doing some work on explainability as applied to reinforcement learning. Maybe if you can share a little bit about that work as well.
Yeah, so I'm the co-director of the UC Berkeley RISE lab, which stands for real time, working on that, intelligent, working on that, secure. So we have an interesting agenda on security, which is another time. And then the E. And there were, for a long time, we're like, what is the E really? What should it mean? And we were initially thinking execution. We're going to execute things securely. But that actually has some bad connotations. So maybe there's another agenda, which actually came out of our exploration in lineage, how we track the relationship between data and the model development process. Explainable decisions would be a good thing to be able to support. And so we had an agenda around how to do, we have actually an ongoing agenda around how to do explainable machine learning by connecting our training process to our data. But what's actually pretty exciting is pulling in some of the recent work in explainable AI. Actually, my thesis advisor, Carlos, has an exciting work, LIME, which provides a black box mechanism for explaining a model's decisions. So my students have been also exploring—
Which has had tremendous staying power. This is, one of the things we talked about 3+ years ago in that early TWIML episode, and LIME comes up all the time still.
Yeah, so I run the risk of another tangent, but the world of explainability is it's kind of rich, and it's created by this need to make sense of models that no longer make sense. And so this idea that I can inspect my model and go, I like how that makes decisions, that's gone, or at least to a first approximation. So we're left with justify the decision you made. Let's go back and at least connect it to the data, to even the input. So my group had started looking at that. And one of the things that we started to ask is, why can't we have some interpretability? And so one of the agendas that I'm exploring that's actually not in the language domain, but more in the vision domain, is how to apply decision trees, to connect decision trees back with our deep learning models so that we can get the accuracy we want, but we can also go and interrogate our model and go, well, it's going to call this a cat, but in order to do that, it has to first identify that it's an animal, and it has to cluster it in animals with legs, and then with fur, and then it gets us to cat. So there is an opportunity to actually understand what the model is going to do at the high level. Each of these decisions is governed by a neural net, so understanding that is sort of off the table. But at least we now have an idea of the decision process the model will go through to make a decision. So this is our recent work on neural back decision trees. When we look at language, it's been an interesting question of what would an explanation look like in the language domain. So there are techniques like GradCam that have been pretty popular in vision that would give us, highlighting parts of an image that say, this is the part of the image you're attending to. We could do that, and there are explorations of that in the language domain. But one of the neat things, going back to our very beginning narrative, is can I connect my decisions back to data? In many cases, that is sort of the ideal explanation. It's like, here's the data that informed my decision about what you've given me now. And so that explanation is what we're exploring. One of the hopes in doing that is you can not only connect it, but you can even fix it. So one of the kind of ideal outcomes of an explainable model is when it gets it wrong, you go, that's wrong. Here's what is wrong about it. And that extra signal could be way more valuable than just some more labeled data. And so that's our hope, and maybe being able to correct our knowledge base if we are referencing data so that we don't use that reference data in the future. That would be one mechanism. In the case of the decision tree, changing the paths. So, cats can't be attached to the thing that are, they're underwater. That doesn't make sense. So I want to move my cat class somewhere else in my tree. So the opportunity to intervene in a model is something that I'm excited about when we look at explanations.
Do you draw a hard line between explanations and interpretability, just when you're speaking about them casually?
I do a little bit because, at least classically to me, I was, again, background being more in the traditional machine learning, we really cared a lot about interpretable models. And that meant that I could look at the individual pieces of the model and start to reason about conditional probabilities, what they would say about the priors that I'm trying to impose on my data. So interpretability to me means something that is sort of independent of the
kind of
query.
Intrinsically.
Yeah, it's intrinsic to the model. Whereas an explanation could also be called a justification, sort of looks retroactively. Here's a decision I made, provide an explanation. If we look at humans are not interpretable. You can't look at their brain. Well, most people can't look at the brain and go, okay, yeah, I know what you're going to do. But they provide meaningful explanations, and that's maybe all we can hope for, and we learn to work with that. My hope with the work and explainability that we're exploring is to sort of provide a little bit more of the interpretability. And I think that's important, one, because if I'm going to deploy a model, I'd like to be able to, in general, understand how it's going to behave, not just on a candidate piece of data. The other lens that we're bringing is be able to adjust the model when it gets it wrong. I want to be able to correct it.
So this work with the decision trees is the set up such that the decision tree is an intrinsic part of, like when you refer to the model there, is the model a superset that includes the decision tree, or is the decision tree a kind of a surrogate model that's used when you're asking explainability kinds of questions?
No, so the challenge here was to make the decision tree the model. So what we're doing, we don't do really crazy complicated things. So in this setup, we're taking a standard ResNet 101 to find an embedding of our input. And then we're using the decision tree as a decision tree on top of that embedding. And so that's allowing us to route our decision process based on that embedding from ResNet 101. So there's a part of the model that I can make no sense of. There's no deep interpretable or even explainable component of that little piece. But there is now structure in how decisions are made.
Right. So the ResNet is basically kind of learning this space of relationships between the things that it's seeing, at least in a computer vision sense. And then the decision tree is on top, making decisions about what is what based on the space that the ResNet has learned.
Yeah. So it is a funny recipe in a lot of vision now. It's take a ResNet-like architecture as a backbone, and its role is to embodying the things. It wants to, but its role is to extract pixel information, to extract texture, shape, things, image attributes that would be then used to make a decision. And it places them in a fairly high-dimensional space. And the decision tree is constructed in a way that tries to use that space to make decisions. Now, that actually alone doesn't work, so you need to take that decision tree and fine-tune the neural net, the ResNet backbone, so that it's compatible with the decision tree we build. So it's a small twist that's needed, but that small twist now allows us to get competitive accuracy to the original model, where you're still using the model, but now have an interpretable path where one of the fun examples is if we give it a picture of a zebra, it's a class we've never seen before, it'll route it down to near the horse, but then it doesn't know what, it'll classify it as something in one of the horse categories. And so it does try to extract some structure to the classes that is semantically meaningful, but also picture in the image domain meaningful. So things that look similar. Yeah.
Mm-hmm. Can you provide a kind of a quick intuition for why a fix is needed in the neural network domain, as opposed to just throwing the existing decision tree against the existing embeddings, and what the kind of intuition of that fix is?
Yeah, so the simple answer is we tried throwing the simple embedding into the decision tree, and it didn't work. The deeper answer is that the decision tree wasn't the neural net wasn't optimized to give features that have some coherent structure that we can build this class hierarchy on top of. And so adding this extra decision tree loss, we can actually force our decision tree to cluster things using semantically similar structure. Like we want horses to be nearby dogs and farther, share less common ancestors to fish. So we can impose some structure in our tree, and then we can force the neural net's embeddings to reflect that structure. So that is why we need to adjust the neural net to compensate or to be able to work in the context of the tree.
So you're changing your loss function in the decision tree to accentuate, kind of like maybe, I'm envisioning kind of spreading out the embedding space or something like that, so that the decision tree can...
So it's more meaningful for the semantics of the decision tree.
Cool. Awesome. Well, Joey, this has been wonderful, learning a little bit about what you're up to there. We still never got very deep into serverless, so we're going to have to put a pin in that one for next time, but very cool stuff. And thanks for taking the time to share it with us.
Thank you. It's been fun.
Awesome. Thanks. All right, everyone, that's our show for today. For more information on today's show, visit twimlai.com/shows. As always, thanks so much for listening, and catch you next time.